not really.
Everywhere there is surface.
And I wanted to thank Misha. He's not here, but I hope he will.
I saw him just running. He left some.
He's run away.
Yeah. But he's
because
around.
he had a very active part in arranging this focused period and inviting participants for the next couple of weeks, particularly. So I wanted to draw your attention to the fact that this week we have extra seminars. We have, in fact, 2 tomorrow. We have Efim Katz at 11:30 tomorrow morning, Dynamics of Pore Formation in Membranes. And we have an afternoon seminar, which is unusual for us. But really, it's an excuse to have a reception after the seminar. So Victor Buchstaber is giving a seminar of broad interest, really, on symmetric quadratic dynamical systems. And that's at 4:30 in the afternoon, 4:30 to 5:30, followed by a reception, just drinks and bites out here. And then on Thursday, we have the usual time seminar from Kerner on self-assembly of icosahedral viral capsids. So we'll move back towards biological applications. Good. Well, this morning it's Eleni Panagiotou and a study of the entanglement in polymer metals. Yes.
First of all, I would like to thank very much the organizers for giving me the chance to participate and learn from this program. And so I will talk about entanglement in polymer melts. So first of all, we'll just give a definition of what a polymer is. Actually, a polymer, the word, it comes from the Greek words polymeros, which means many parts. And this is exactly what it is. It is a macromolecule of many repeated units, which are connected together by covalent bonds.
Is it on?
Yes, it should be. Mostly talking.
Okay, good.
Okay.
Put it in your pocket.
You could put the
Transmitter.
This doesn't fit. Okay. I can.
Attached to your belt.
Okay, so these macromolecules, they may have many different architectures, and in this talk we will focus only on 2, which is linear or ring. And linear architecture, we mean that these are, we will call them also open chains. That means they have a beginning and an ending point that are distinct. Or ring polymers, we will call them closed chains. And these architectures, they cannot be changed because these bonds that connect these monomers, they cannot, they have to break in order to allow for a polymer chain to cross itself or pass through another chain. So examples of polymers are the biopolymers we meet in nature, like DNA, or polymers that can be built in a laboratory, like polyethylene, and actually all the plastics we use are made by polyethylene and similar material. So these materials, they have very interesting properties, and this is why they are widely used, and their properties are very related to the conformation of these chains. So if we have ring polymers, then of course we can, this will, with as the chains get longer and longer, this will be knotted with probability 1. So their conformation is significantly affected by knotedness, and this can be measured by using then the notion of topological entanglement and study it by using tools from knot theory. In knot theory, then we know what the knot and link is, and we can distinguish between different knot and link types. And in order to do this, we usually use knot and link diagrams. So we have a knot in space, or link, we project it, and then we study if 2 diagrams are equivalent. Then they can be related by Reidemeister moves. And then very many knot invariants exist that can be computed on these diagrams, and they are very strong in distinguishing the different knot types. But very often in polymers, and especially in polymer melts, we have linear polymers or mixture of linear and ring polymers. And there, of course, there does not exist the notion of topological invariance or topological equivalence, since we have open chains, and with time they can be deformed, continuously deformed in space, so that they are no more entangled. But in experiments, there is a notion of entanglement in the sense that, so if we have there is a material like the kids play with, a deformable mass, they can make a ball with it and then throw it on a table and it bounces back like elastic material. But when you leave it on a table, then it flows like a liquid. And these are the viscoelastic properties of polymers that make them so interesting. And they are very closely related to entanglement, because the chains, for some period of time, when they try to move, they feel these topological obstacles because of the presence of the surrounding chains. But after some time, they realize that they are actually free to move, so they start to flow. So a very successful model to describe this motion of the chains has been the tube model, which suggests that the chains are moving in an area of fixed obstacles, which create like a tube around the chain, and so the chain can move, can explore for some time the space around inside the tube. But then, in order to move, it has to substantial time has to pass until it realizes it can only go ahead by moving along the tube. So we see the notion of topological of entanglement here is related to these local topological constraints, that these barriers that the chain moves to its meets to its movement. So okay, how can we measure that using tools from knot theory? One approach is to close the chains, and first scientists try to just do this direct end-to-end closure and define the knot link type that arises. And of course, this is not well defined, because if we use another closure arc than the one shown in the figure, then we can get a non-knot. So this is why Professor Millet, Dobé, and Stasiak, they proposed the statistical method of defining a knot type, and we have heard about it in other talks by Professor Millet and Professor Rodon expanding this method. So what we will do is we will not close the chains, and we will try to consider the chains as frozen in space and apply a measure of entanglement directly to the snapshot that we see, the configuration that we have in space. And a measure of entanglement that can be applied directly to open curves is the Gauss-Linkin integral. So for closed curves, this is we know it is the half algebraic sum of crossings in a random projection direction between the two curves. Projected curves. Then also it is equal to the intersection number between the one curve and the Seifert surface bounded by the other. All these interpretations, they also coincide with the Gauss-Linkin integral that was introduced by Gauss. So this integral, it is exactly the average half algebraic sum of crossings over all projection directions. Well, when it is applied to closed chains, of course this is equal. The half algebraic sum of crossings, it does not depend on projection directions. So this average reduces just to this number. But when we have open chains, then this half algebraic sum of crossings depends on projection direction. So we do have to compute this average over all possible projections, and it's like an expected value of this linking
Dots
integral.
means derivative over time, dots. Gamma 1 dot, gamma 2 dot, what does it mean?
It's just the tangent vector to the
Derivative with
curve.
respect
Yeah,
to
along the
Derivative, yes.
length.
T or S. Yes, it's
Yes, it's-
derivative.
Where gamma 1 and gamma 2 are the arc length parameterizations of the two curves we have. So this might at first seem like bad to have to compute this integral, but it is not when we have polygonal chains, as in the case of these polymer chains, because then we can compute it very easily just by knowing the coordinates of the vertices and using this simple just dot products and cross products. this is a measure of how much the two chains are wind around each other, because we understand that if they lie if they are really far apart from each other, then in many projections we won't see any crossing, and then when we see crossings, most of them cancel out on average. So then we are interested, this was for a frozen configuration. Now when we see what happens as they move in time, this is a continuous function, and you see how it changes when the chains open by a small distance. Also then, we know that the linking integral for two unlinked curves, it is exactly equal to 0, but for open chains, this may not be 0 even if the chains are very far apart from each other. This might be a good characteristic, in fact, because the entanglement in these physical systems depends on the distance. It is something that concerns the distance of the chain. So maybe this could be interesting. And also we can use this integral to compute measures of self-entanglement, the average crossing number, the right or the self-linking number. So these polymer chains can be seen like random walks of certain step size of bond lengths or bond angles which are specified by the chemistry. And it would be very interesting if one could predict for a given type of random walk or polygon what is the expected value of the absolute linking number of that random walk for a given length. And actually this type of theorems are very difficult to compute, even how this measures scale with the length of the chains. A very simple model is that of equilateral random walks, which are random walks with no bond angle restrictions, but always fixed length. And and they are in free space. And then we can also simulate random walks in confined spaces, which is something that occurs in applications. And there exists a very simplified model of uniform random walks and polygons, where each vertex is chosen in a cubic cell with the uniform distribution. Then one can prove that for a uniform random walk, so two uniform random walks of length n, the mean squared linking number goes as O of n squared. And similarly for the mean squared self-linking number and mean squared right. But it is more interesting to prove how scales the mean absolute linking number. And the numerical results show that it grows linearly with n. And it is interesting to see that for equilateral random walks, the same quantity grows as the square root of n. So this very interesting, very simple measure of entanglement, this linking number for open chains, which is not a topological invariant, we see that it captures some difference between the different systems, some substantial difference that concerns their conformations. Okay, so this is when we have two chains in free space or one chain in free space. But we are interested in what happens in polymer melts. So in polymer...
I was wondering what the definition of a uniform random walk was.
Each vertex of the random walk is chosen with respect to the uniform distribution in a cubic cell.
Okay.
So it's bounded then.
Sorry?
It's in a bounded domain.
Yes, it's confined. It's supposed to simulate confined random walks. It's very simple. So then when we so our goal is to measure entanglement in polymer melts. Then polymer melts are composed by thousands of chains. And actually for their simulation, one has to use periodic boundary conditions, because it is impossible to simulate, to do a molecular dynamic simulation for such a large system. In that case, one uses a cubic, in general, a cubic simulation box where the chains are inside, and then when a molecule touches the faces of the box, it re-enters from the opposite face at the same position, well, a translation of the same position. And then when we glue these cells along their faces, we can form an infinite periodic system. And this is actually the material that we simulate. So if we want to look at the conformations of this material, then what we have to look is at something that looks like this. So this is like a projection of a two periodic boundary condition system. And so we want to measure the entanglement of all that. And by definition, this is infinite. But we will, even if we consider that we will take a finite collection of such cells to measure this entanglement, then we will have we notice that we have many repetitions of the same configurations. So we will have to compute many things at the same time, the same thing many times. On the other hand, so we want to extract a pattern from all this periodic system so that we don't have to compute something again and again. But we know that all the entanglement is created by this cell. If we had to focus on, if we just take this cell and try to measure entanglement in this cell, then we have just these short arcs. And these short arcs, they would not capture the higher degree of linking that is created by the global geometry of the chains in 3 space. So we need something different. And so we give some definitions, and we call a generating chain the arcs inside the cell that are connected in 3 space to form connected components. So these arcs are one chain, and these blue arcs are another chain. We call them generating chains. And then all the collections of the copies of these generating chains, we call them free chains. So all the blue curves are one free chain, and all the other red curves another free chain. And we will define entanglement between 2 collections of free chains. So we define the periodic linking number as the sum of linking numbers between an image of the one free chain I, say I1, and all the images of the free chain J in the periodic system. Similarly, we define the periodic self-linking number as a sum, as the self-linking number of one image of I, and plus the linking numbers of I1 and all its periodic images. So, if we see,
Can I ask you just one question? All your components are closed curves in R3, but as you've described to some of us before, you might also have curves that are just closed in the torus. So you're excluding those from the definition?
yes, yes. We are only looking at compact curves, if that makes sense. I mean, they are finite curves, finite length. And so then we have defined the periodic linking number of the 2 collections, blue and red curves, as sum of linking numbers between I1 and all the red curves. So of course this captures all the topological constraints that an image of I of the blue curves feels because of the presence of the red curves. And this is independent of the image we look at. If we move anywhere else in the periodic system, we will see the same thing. Also, we notice that it is independent of the size and the shape of the simulation box. It is directly computed in the periodic system. So for closed chains, this infinite summation introduces actually to a finite summation. It is equal to the sum of linking numbers between an image of I and all the images of J that intersect its ciphered surface, because all the others have linking number 0. And also it is an integer in the topological invariant, and if the chains lie entirely inside the cell, it coincides with the Gauss linking number of the 2 chains. Let us suppose that we have an image I1 and an image of the other chain J1. So on each one of these 2, we define a base point on each one of the generating chains. So then this base point exists in any other translation of this generating chain. So we can define this linking number that we had at first between I1 and all the images of J in the periodic system. We can express it with respect to J1 plus a translation vector that connects their base point, the base points of J1 with any other of its translated images. So we notice that this, of course, forms a lattice in 3 space, we can imagine. So I'm just using 2 periodic boundary conditions because it's easier to visualize. But actually, so we are adding terms, and all these terms correspond to lattice points in 3 space. And we notice that if we define one vector, then all the lattice points that lie on this line, they can be defined as multiples of this vector. So we can rewrite this summation as a summation over all the vectors whose coordinates greatest common divisor is equal to 1, and then take multiples of this vector to take all the lattice points along one line. So we have rewritten this expression like this, and then finally we can split the term of the linking integral between the pairs of edges that compose the chains. So finally, we are interested in this to prove convergence of this expression where Li and Lj are just two pairs of edges. Okay, so we have this situation. Let's denote by alpha the vector that denotes the base points of the two edges. And then we want to prove convergence, so let's focus on the case of one periodic boundary condition. So we take all the lattice points along one line, and that is defined by one vector. So then the scaling of the Gauss-Linkin integral with respect to the distance of the two edges, we can say that it grows as O over 1 over the distance of the base points squared. So then this is enough to prove convergence when we add all these terms along only one direction. When we try to apply the same technique in the case of two periodic boundary conditions, then we have to prove convergence of this series, which we can't. So we have to take into consideration, so we notice that before what we proved was the absolute convergence of the periodic linking number in one periodic boundary condition. That is, we took the absolute values of all the terms. Now we have to take into consideration cancellation of signs. And actually, we notice that all the opposite translations, except of one case that can be induced in the case of one periodic boundary condition. So in this talk, we would say for all opposite translations, the opposite translations have opposite signs. So actually, when we group together these terms, this gives us a difference. This summation is a difference. And it is equal, we estimate that this difference is equal to the linking number between one pair and then the translation of one edge of the pair by 2 alpha, where alpha is the vector that connects the base points. So the difference of these two linking numbers that correspond to these two lattice points is equal to the sum of these two, is equal to the difference of these 2 points. And then we prove that for all vectors whose norm is larger than a natural number, the square root of a natural number, then we can estimate exactly how much this difference is and show that it is grows as 1 over the distance to the cube, to the third power. And then this is enough to prove convergence in case of two periodic boundary conditions, because for all the terms that are whose norm is smaller than square root of n, 0, then this is a finite number, and all the rest we have in the scaling that we need to prove convergence. But then if we try to use again the same technique for the case of three periodic boundary conditions, we can't, because we arrive at this series which we do not know if it converges. And we have to find further cancellations. But we can imagine that, so we notice that the opposite translations, they have opposite sign. And we computed their differences and took the absolute values and of these differences and did the sum. But these differences have also sign. So if we took that into consideration, maybe we could prove convergence in three periodic boundary conditions. But this is not easy to prove in the general case. So we find some special configurations like the one we show here. And for this one, we can prove convergence as follows. So this is a configuration where the vector alpha that connects the base points is parallel to the cross product of L1 and L2 and also parallel to the x-axis. Then we group together for each vector, we group together all the vectors whose coordinates are permutations of the coordinates of the one vector. And then finally we prove that many of these are just mirror images, and so they are the same, and it suffices to prove what happens when we add together all the vectors which are rotations, whose vertices are rotations. And we prove that when all the coordinates are much larger than alpha, then this can be approximated by 0. So that means that for all the vectors that lie in this infinite, let's say, a cube or infinite area that starts for V1, V2, V3 much larger than some k, then this is equal to 0. And then for the rest terms, it is a finite number of planes that we can treat like the case of two periodic boundary conditions. And so we can prove convergence for this special configuration. But now we want to see this for a random configuration because again it's not enough. So then we regroup the elements again, and now we sum over n the natural numbers in the following way. So we go on the lattice in the sphere in 3 space, and we consider a sphere of radius square root of n, and then take all the points that lie on the sphere of radius square root of n, which are whose greatest common divisor is equal to 1. This is exactly the number of primitive representations of n as a number as a sum of 3 squares. So we group all these terms together, and for each one we take all its multiples. So this is what we take for each n, and so this we define it for a random configuration x that we denote x. We define this as a function fn of x. Then we have proven that the sum over n of fn of x0, where x0 is the previous configuration, it converges. We find then a path in the space of configurations that takes us from x0 to any other configuration, and we prove that the derivative of fn along this path, it grows as O of 1 over the distance to the 4th power. So then this is enough to prove convergence, because the normal vector v to the 4th power is equal to n squared, and then the number of primitive representations of n as a sum of 3 squares is approximately equal to the square root of n. So that converges, and then by fundamental theorem of calculus we can prove convergence for a random configuration. So okay, this is satisfying, because now we know that this measure that we defined can be applied to open curves, and it has the nice properties that the linking number had. But actually we want to compute it in, we want to be able to compute it, and this is an infinite summation, so this is not very useful. That's why we define a cutoff of this, and we call it the local periodic linking number, because as we said, what is interesting in the application is to capture these local topological constraints. So for an image of I, we take all the images, only the images of J that intersect the cubes in which I1 lies. So these are the only images of J we take. So this is not just a random cutoff. This is such that we take the less number of images needed in order to give a symmetric measure of entanglement. So then LKJI is also the same. If we open a J1 and take all the images, the blue curves that intersect its cells, then it will give us the same answer. And this may not be a topological invariant even for closed chains, but this would need, we can find such examples, but this would need the chains to be very long with respect to the size of the cell, and this is not what we will use in the applications. So we can consider it a topological invariant for the systems that we study. And okay, I will skip that and go directly to the application to polymers. So this is what we propose to use to measure entanglement in polymers, but polymer physicists have been using their own methods so long to measure entanglement, and these consist in algorithms which try to reveal the geometric characteristics of the chains. There are 3 such algorithms similar, and one of them is the Creta algorithm, which for each it works as follows. So for it starts for a configuration. Let's say we pick 3 bits and then we align them if there is nothing between them. And then we take more bits, we align them and continue until until we reach, it becomes either a straight rod or it reaches it finds some obstacle. So I'll try to show this how it works. Okay. So this is 3 simulation periodic box where you can see the application of the Creta algorithm. So as it does this process, then at some point where it cannot move anymore, it shrinks the bit diameter and enters some extra bits because of the shrinkage. There are some gaps, and continues that until some minimum thickness is achieved. which is defined by whatever someone wants for that.
Is this a bit like reducing energy?
There are two geometric methods, Creta and Z1 algorithm, and then there is a primitive path analysis algorithm, which I have not really studied it, but I think it just consists in lowering the temperature of this in this molecular dynamics simulation, and then for some reason the system the chains get to form this network. But all these algorithms, it is very interesting that they give different results, but not very different, but not the same. So
yes, exactly. It's non-unique.
Yes, it's non-unique.
When there are open ends.
Yes. Yes. So let me.
Why is it they're getting thinner in cross section?
Yes, because in order to continue this shrinking.
Oh,
Yes.
you're feeding that in. Yeah.
Okay. So we notice that these motions, they are like Reidemeister moves. So if the chains were closed, we would not expect to see any difference when one applies this algorithm. But we have open chains, so we don't know really what is going on by the application. So we will use this periodic linking number to see how it changes before and after the application of the Creta algorithm. And here are the results. Here you can see the probability distribution, the normalized probability distribution of the periodic linking, local periodic linking number for the chains, the original and the corresponding reduced chains. And you see that there is a large overlap between the two distributions. And here you can see the probability of the differences, which is very narrow, around 0. Then we computed when we close the chains before and after the application of the Creta algorithm. So the closure happens before and after and not during the application of the algorithm. So if it happened during the algorithm, it should be invariant. But here we see that there is a smaller overlap of the distributions and larger differences. So this suggests that during this reduction process, the chains cross this imaginary closure arc. So even for these motions that are respecting the topological constraints, we see that the random closure method, the end-to-end closure method is not so good. Doesn't give good results. So then we check just the difference between open and closed chains, and we see that the differences are much larger. The similar for the reduced chains. And also we do the same for the local periodic self-linking number. And we see here that this is very different. These are the reduced chains and these are the original chains. So the periodic self-linking number is equal to the self-linking number of a chain plus the linking with its own periodic images. And we see that the linking with its images, it's not so significantly affected. It is the self-linking number that changes because, of course, the torsion of the chains is significantly altered by the algorithm. So this is something that we expected. Okay, and right. So we saw how we can measure entanglement in two chains in a periodic boundary condition. That was two infinite chains in a periodic system. But what we want is to measure entanglement of the entire periodic system, and this is formed by many chains in a simulation box. So we propose to define a linking matrix, in the case of periodic system, a periodic linking matrix, whose elements are the periodic linking numbers of the chains, and the diagonal elements, the periodic self-linking numbers. Then we can see that if we have one cell, and we have and corresponding linking matrix LMC, then if we concatenate k cells, then these k cells, we glue them together, they will generate the same system, but their linking matrices are different. So we will look for characteristic values of these matrices that are invariant of cell size, and so we expect that these characteristic values, they will really concern the periodic system and not be affected by cell size. And here we see some examples. If we have this case of one chain in one periodic boundary condition, then this is a trivial one-by-one matrix. The self-periodic linking of that image is equal to 2. And then if we glue two cells like that, then we have two chains in this cell. But the system that they generate is exactly the same. But by our definition, this linking matrix will now be 2 by 2, different than the matrix we had for the one cell. And then if we concatenate 3 matrices, this is a 3 by 3 matrix. But we see that all these matrices are similar to a matrix which has an upper triagonal form. And we see that the first block, this 1 by 1 element, is the same. Similarly, we do another case a bit more complex of 2 chains at first, and we see again that the matrices are similar to a matrix of upper triagonal form with this first element. And actually we can prove that the linking matrix of M cells is equal, it has this form where this matrix is the matrix of the first cell. That means that the eigenvalues of the linking matrix are invariant on cell size. But well, some of the eigenvalues of the linking matrix. The problem is that we do not know yet which are the eigenvalues. Is it the largest eigenvalue that is invariant or not? So this shows that it might be good to look at the eigenvalues for properties of the periodic system. And then we propose to use graphs in order to get more information about entanglement. So, of course, this linking matrix, it suffers from the problem of the linking number, that it is a pairwise measure of entanglement. But nevertheless, we will see that we can, with the approach, with approaching it by graphs, we can extract some information that we cannot get just by looking at the pairwise linking numbers, like the homogeneity of the entanglement. And we will try to relate homogeneity to the connectedness of the graph. And measures of connectivity are, a measure of connectivity is the trigger constant, which tells us if there are two collections of vertices with heavy weights and that are not well connected to each other. So I forgot to say that each vertex we consider that it is a polymer chain, and then there is an edge that connects two vertices if the linking number is greater than 0, and the weight then of the edge is equal to that linking number. So we will do a simple test case with equilateral random walks. In the first case in a system with 3 periodic boundary conditions, in the case of length 100 and length 200, and then 2 cases of a system in 1 periodic boundary condition where we have 2 layers that of chains, in which case the first they intersect by 50%, and in the other case they do not intersect at all. So it is a totally disconnected system. And here we see how we do that for different systems at different cell sizes. And first we look at the asphericity of the eigenvalues, which shows how much the eigenvalues are different from each other. And we see that for the systems that are in 3 periodic boundary conditions and they are uniformly linked, it tends to similar value. And in the case of the system that is by 50% overlapping, we see a slightly different value. And then for the system which consists of 2 different layers of chains, we see a small difference but a clear difference between this asphericity. Then we compute the trigger constant, and for the totally non-overlapping system, it is always equal to 0, as it should be. It's not shown here. And for the system with 50% overlap, we see it is much smaller than the systems which are normally uniformly linked. But the trigger constant is very hard to compute, so we use the Laplacian and its eigenvalues to provide boundaries of the trigger constant. And we see again that we have that again, it distinguishes the non-overlapping system, the one that is non-homogeneous, by the homogeneous systems. And similarly, there are other measures like the maximum eigenvalue of the Laplacian, which can detect if a graph is bipartite or not. These are our studies, and the conclusions we have are that the periodic linking number is well defined, and it can be applied in a theoretical setting, maybe in a non-equilibrium dynamics formulation. And also we saw that the linking matrix captures some characteristics of entanglement that cannot be obtained just by looking at the linking numbers. And also that Greta retains the linking information. So I'd like to thank you very much for your attention.
Oh, thank you. Very interesting. Do we have any comments? Yes.
Sorry for my probably stupid question. What kind of random walks you use? It's three-dimensional space, and after each collision, particle can move with equal probability to any direction, or how it's distributed? What?
So in which case, because
it depends.
so this was just random walks, really no dynamics. But the one with the Greta algorithm, that was polyethylene chains. So if that was your question, or which part?
The question was about details. I'm not interested.
So for the polyethylene simulation, I did not do it, but I think that it is similar to this simulation of Fene melts, where one considers the
Are you talking about molecular dynamics? What kind of molecular?
Well, I think that for this data, it was not used. It was used a combination of molecular dynamics and Monte Carlo, because in order to have equilibrated conformations, the molecular dynamics are not. It doesn't work. So yes, but the others were just random walks simulation, no dynamics at all. The last part.
Yes, Rob.
I mean, I want to go to your eigenvalue conjecture and to understand it. I'm wondering, is there a way to make your linking matrix converge to some operator that you can actually then study the eigenvalues of in a direct way? It's a limiting large-scale linking matrix or operator. Like I don't know, like a Toeplitz operator or something like that. Is there a way to take a limit?
Well, we can, for this linking matrix, we can prove this, but we don't know what. We should find what D and D look like. These matrices, but it is not so clear. But that's how far we can go right now to see what would the random matrix look like.
I suppose.
I thought it was just to see if you could avoid the sort of issues of the finite dimensional thing and get around that. I don't know.
It sounds interesting, but I have to discuss it.
I suppose the longer term purpose of this work is to extract information about the actual physical properties of
Yes.
a polymer melt. For example, its stress-strain relationship.
Yes. Actually, this is so we.
And dynamics. You mentioned dynamics.
Yes.
Reptation is dynamic.
Yes.
How I could interpret this linking?
Yes,
Well,
because it's for different topologies, different sets, different linking matrices
Yes.
or whatever. What difference does it make?
Yes.
Yeah.
Well, for the dynamics and all these characteristic times and for all the different scalings that polymers show, they are related to this critical mass, critical molecular weight. And actually, this critical molecular weight is exactly the molecular weight of this strand, of a strand that connects to entanglement, which is actually related to the bit diameter. And so This is actually a very important key quantity, the distance between entanglements. And yes, this sounds quite abstract, like what can we do, but actually right now we are using the right in order to obtain information about this, and our preliminary results give an estimation of NE that is quite in good agreement with experiments. And if that would work, that would show that these measures can give important information.
Very good. Well, thank you again, Eleni.
Thank you.
Very nice.